then waiting for record to kick in. And I'm waiting for it to confirm that it's booyah. Okay. All right. Yeah. Right. I want to talk a bit about the theory that probably revolutionized all of the earth sciences more than anything else has in recent years. After I admit one more person. And that's the theory of plate tectonics. And it ultimately explains why the oceans are where they are and why they look the way that they do. We can define 5 main oceans, the Arctic, the Antarctic, the Atlantic, the Pacific, and the Indian. I'm hoping you know world geography well enough to be able to tell those apart. There's some shallower and somewhat restricted marginal seas that we can define. The Mediterranean's one, the Baltic Sea is one, the Red Sea is another. By the way, that scale, bathymetry, that just means how deep is it. So if you've ever felt like Irving Berlin and wondered how deep is the ocean, well, there you have it. The deepest part of the ocean is 11,000 meters. That's something like 36,000 feet below sea level. The highest mountain in the world is roughly 29,000 feet high, meaning that in theory, you could sink the highest mountain in the deepest ocean and it would not break the surface of the water. I mean, it might break the earth if you pick up a whole mountain and rip it up and move it. And anyway, don't try that at home. But yeah, the deepest ocean is deeper than the highest mountain, which sounds like a song lyric. If you look at the geography of the bottom, if you were to go to your favorite beach and just start wading out, and assuming you had, big air tank and training so you didn't actually drown, you'd walk for some distance along a relatively flat, shallowly sloping area called the continental shelf. That only slopes downward roughly 1 degree. And it's showing up here in this colorized map as that area in light blue. So you can see that there's, if you can find Florida, you can see there's a pretty wide continental shelf on the Gulf of Mexico side of Florida. There's a big area of continental shelf that's joining Alaska and Siberia. There's a wide continental shelf area going up the North Atlantic. You can see that there's a wide continental shelf area in Northern Europe surrounding Britain and going all the way to Scandinavia and so on. All of those flat-looking areas that are shaded light blue is continental shelf. And that goes all the way to an area that slopes down much more deeply. It's not that much. The slope downwards is roughly 2.5 degrees instead of 1 degree. And it's not quite as steep as it looks in this picture because they've exaggerated the vertical relief for clarity. If you could actually take the Earth and shrink it to the size of a pool ball, it would feel as smooth as a pool ball. The highest mountain is, roughly 7 miles high, but the diameter of the Earth is like 7,800 miles, 7,800 miles thick, meaning that the highest mountain is only 1/1000th of the total the total diameter of the Earth itself. When you would have a hard time even feeling that. If you could shrink the Earth down to the size of a pool ball, the highest mountain would be, microns in size. Still, anyway, it's exaggerated a bit for clarity, but the continental slope is where the shelf leads off, and the continent slopes down to the deepest bottom of the ocean, a zone called the abyss, the abyssal plain. So there's another view of it. This happens to be the coast just off of Monterey, California, just visible at the upper left. That's the very south end of San Francisco Bay. That's where San Jose is, or if you say it, if you're from there, San Jose, right? It's like one word, San Jose. Then you can see some mountains of the California Coast Range. There's Monterey, California is kind of up in the top center, and that black line marks the shore, where the beaches are. And you can see that extending some distance away from the beaches, you have continental shelf, and you can see where the continental shelf ends, and the continent slopes down to the abyssal plain. And the continental slope in many areas is cut by submarine canyons. You can see a very prominent one starting right where Monterey, California is, and dropping, cutting a slice through that continental shelf. Okay, you with me there? Okay, the continental slope descends down to a slightly shallower zone called the continental rise, and then drops all the way down to the abyssal plain of the deep ocean in places like, let me see, this is about 5,000 meters deep in the Atlantic. That's roughly, what, 17,000 feet. In the middle of the Pacific, it may be 20,000 feet or more. And it is pretty flat, although it's periodically interrupted by occasional seamounts. That's basically like mountains, but the tops are underwater, so they're not islands. They're seamounts. And if you were to walk along the abyssal plain, occasionally you would hit a feature called a mid-oceanic ridge. And you might encounter an oceanic trench as well. I'll show you what those look like in a little bit. What the heck? Why wait? If we go back there, if you can find the Atlantic, you can see, gods, I hope you can, the North America, South America, Africa, and Europe in the middle of the Atlantic. And running right down the middle of the Atlantic, right here, like a seam on a baseball, that thing is the mid-Atlantic ridge. That is the equivalent of an extremely long mountain range. It's not tall enough to break the surface of the ocean, except the one place it does come out onto land is Iceland, right up here. It's the only place where you can walk across it. It's great. The place where the mid-oceanic ridge comes out on land happens to be the valley where the Vikings used to hold their assemblies, which I guess is kind of neat. Anyway, that's the mid-oceanic ridge. And in other parts of the ocean, like here, you can see this very dark area is an extremely deep but narrow zone called a trench. That one specifically that I pointed to is called the Marianas Trench, and it's the very deepest part of all of the ocean. So if you could walk along the abyssal plain, it would mostly be pretty flat. You would periodically hit seamounts, And right in the middle of the Atlantic, you have this mid-oceanic ridge. It's actually a double ridge with a valley cutting right along the ridge line. I didn't explain that very well. Instead of one long ridge, if you were to climb up to the top of it, you'd get up to the top of the ridge and there'd be a deep chasm. And if you could jump across that, you'd get on another ridge and then descend back down. I think there's a slide coming up that might make that a little bit more clear. So the question is, why does it look like that, and what is all of this stuff doing? Back in the 1800s, it was usually assumed that the deep ocean was simply a place where absolutely nothing ever happened. The guy who made us realize that it's much more exciting than that is this guy, Alfred Wegener, a Austrian geophysicist, did a lot of work in different areas. He pioneered the use of balloons to study conditions in the upper atmosphere, weather balloons. He did work on astronomy, did work on physics, and he came up with this goofy idea that maybe, just maybe, the continents of the Earth weren't fixed in place. The original idea was the continents were fixed exactly where they were and always had been, but parts of them under very, very long geological conditions might flex up and down, which explains why you can find fossils of sea creatures in Iowa, as I used to do when I was a kid. Why you can find fossil crabs and squid and things like that in North Dakota. The old explanation was that that was because the continents were flexing, and occasionally parts of them would bend down and parts would get pushed up and make mountains and so on. Wegener said, hey, no, I've got a better idea. What if the continents are moving? At the time, it seemed crazy. Not a lot of people liked his ideas, but it turned out he was right. And people didn't realize why he was right until beginning in the 50s. The US started doing an awful lot of research into the deep ocean in the 1950s, using a ship like this one, the Glomar Challenger, which sailed around the world collecting rock samples. You see it's got a drill rig right on its superstructure, studying the structure of the rocks that underpin the oceans. By the 70s, a submersible called the Alvin had been invented that could actually go down and study these things directly. You could actually send people down to some of these very deep, deep regions, although the Alvin can't go all the way to the very deepest. But we have a lot more data than we used to have about the rocks that make up the deep ocean. By the way, the Glomar Challenger's real mission was to salvage wrecked Soviet submarines and steal their code books, which they succeeded in doing at least once that we know about. And a lot of the reason we were doing all of this research into the deep ocean was not for, the noble pursuit of science. It was because this is when we're figuring out how to put nuclear missiles on submarines, which ensures that even if the Soviet Union completely nukes North America and we all die in a radioactive holocaust, at least our submarines can pop up and fire a deadly barrage of missiles at the Soviet Union, which I guess will be some consolation except for the fact that we'll all be dead. Right, anyway, and if you're going to have a fleet of submarines, you've got to know what is under the sea. It would really suck if your very, very expensive Los Angeles class fast attack submarine crashed into an undersea mountain that you didn't know was there, right? So a lot of this research was funded directly or indirectly by the Navy. They're looking for places to hide subs, places to hide undersea cables so they couldn't be tapped, places to tap the other guys' undersea cables, places to screen various, listening devices and things that they don't want to know anybody about. There was a lot of defense money that was flowing in here. And since the Soviet Union hasn't nuked us yet, I assume it's paid off, maybe. But quite aside from that, we've learned a lot about the structure of ocean basins, and it's this that I want to focus on. The reason why you have continents and oceans in the first place is that the rock that makes up a continent is just a little bit lighter. It averaged 2.6, 2.7 grams per cubic centimeter. That's roughly the density of a continent. The rocks that make up the bottom of the ocean are just a little bit denser, 2.8 grams per cubic centimeter. That, by the way, is why the legend of the lost continent of Atlantis probably doesn't work. Now, Atlantis may have been based on some volcanic islands that blew up, because that has happened. But you're not going to get an entire continent sitting in the middle of the ocean and then dropping into the ocean for the same reason that you're never going to have an ice cube in your drink spontaneously fall to the bottom, right? Ice is lighter than water, so ice floats, yes? Continents are lighter than oceanic crust, so continents bob up. And continent and oceanic crust are both less dense than the rocks that lie underneath them, which are, I think, an estimated 3.3 grams per cc. Okay, you with me there? Wegener's original idea was called continental drift, and you might have heard that term. The theory that we've built up beginning in the 50s is called plate tectonics. And the idea is that the Earth's crust is divided up into slabs of both continental crust and oceanic crust. And they form tectonic plates, roughly 20 of them, if memory serves. And the ocean crust is down and the continental crust is up because the continental rock is a bit lighter. But both continental and ocean crust are less dense than the layer underneath, which is called the asthenosphere. So kind of hard to say with a mask on. Asthenosphere. Asthenos, by the way, is Greek for weak, as in not strong. Another name you'll see for it is the upper mantle. And it's solid, but not exactly. Under very, very slow, long time scales, it flows. So if you were to actually try to dig down there, I mean, the heat would probably kill you. But if you could magically survive that, it would look like solid rock. It's very hot, but it's also under very high pressure that keeps it solid. But over very long time spans, it bends and it flows. There's convection in the rocks of the asthenosphere. So you could think of this as being something like extremely sticky, thick peanut butter. All right, and riding on top of that, we have the plates. You can see we're on the North American plate, which also includes Greenland and a little piece of Russia. The Pacific plate is the floor of much of the Pacific Ocean. The Eurasian plate is most of Europe. The African plate is most of Africa. There's a number of small plates, like the Juan de Fuca plate and the Cocos plate, and the Caribbean plate and the Scotia plate. It's now parts of the Eurasian plate, but China used to be on a separate little tectonic plate many millions of years ago, so the Earth used to have a China plate. Get it? China plate. Tough audience. Here's the thing, where plates come together, you tend to get a lot of earthquake and volcano activity. This is some old data, but it shows the point very well. These are the epicenters of earthquakes greater than magnitude 5. Loosely translated, that is strong enough to knock things off shelves or stronger. Each red dot is an epicenter, and you can see that those dots trace the margins of the continents beautifully well. Not the margins of the continents, the margins of the plates beautifully. You can see there's a whole bunch of earthquake epicenters all down that mid-Atlantic ridge I was showing you right there. There's a bunch on the edges of the Pacific plate right there. This is all the Pacific plate. There's a bunch right here where a plate called the Nazca plate joins the South American plate. Now, there's a few that are outside of that system. Hawaii, for example, is right here smack in the middle of the Pacific plate. And later on, we can get to why that's the case. I don't know if it's today, but at some point we'll talk about what makes things like Hawaii, which have earthquake activity nowhere close to a plate margin. But the vast majority of earthquake activity, and incidentally volcanic activity as well, is associated with the edges of tectonic plates, where the plates are touching each other. Okay, here's the thing. We've got abundant evidence that the plates are moving. They're not holding still. There's a few areas, I'm going to back up a little bit, like up here where the North American plate touches the Eurasian plate. That boundary seems to be pretty quiet. There's not a lot going on there at all, as far as I know. It's hard to tell, though, because it's a very difficult area to reach. It hasn't been studied a lot, but most of the plates are moving relative to each other, and two plates can do one of two things. They can make like the Beatles and come together. Right now, over me. Sorry. They can come together, or they can pull apart, or guess what the third option is? Yeah, or they can slide past each other. They can move side to side. In a few parts of the world, they might just sit there and do nothing. But just about everywhere, they're either sliding past each other, moving apart from each other, or coming together. Wherever you have two plates are moving apart, we call that a divergent plate boundary. And along those boundaries is where you find a mid-oceanic ridge, like the mid-Atlantic ridge that I was pointing out a minute ago. That's an area where plates are pulling apart. Wait, if they're pulling apart, how do you get a ridge? I'll show you. When two plates are coming together, what happens depends on what type of crust it is. If you have two chunks of continental crust, that relatively light rock, crashing into each other, you get a particular type of mountain range forming called a fold belt. The most famous example right now would be the Himalayan mountains. India used to be a separate, smallish continent of its own. It crashed into Asia something on the order of 20 million years ago. And the rocks of India and the rocks of Asia have both been buckling like the buckling like the hoods on two cars that have hit each other head on. and throwing up the world's highest mountain range, the Himalayas. You actually know what this looks like because, roughly 280-ish million years ago, what used to be the core of North America crashed into what at the time was a separate continent called Gondwana and threw up an enormous fold belt mountain range that would have rivaled the Himalayas. And 280 million years later, we're living in the eroded ruins of it. This is the Appalachian Mountains, which actually used to be connected with the Ouachita Mountains. If you've ever driven around and looked at places where rocks are exposed, most of the rock layers around here are tilted. And in some cases, there's a place you can see this in hot springs. They've been crumpled. You can see that they actually, what used to be flat rock layers are now bent into arches. That's what happens when two continents collide and their rocks just crumple up against each other. Yeah, the Ouachitas have eroded a lot, but they used to be possibly as tall as the Himalayas are now. And they resulted from the same reason, two areas of continental crust going smash against each other and crumpling those rock layers and folding great big folds in them. So the Appalachians, the Ouachitas, the Himalayas, the Ural Mountains between Europe and Asia, those are all fold belts. Where a continental plate runs into oceanic crust, what happens is the oceanic crust sinks under the continent, and we have what's called a zone of subduction. Watch the spelling. There's a B in there. Subduction. The geological term for the process of building mountains is orogeny. O-R-O-G-E-N-Y. And time was you could get t-shirts at geologist convention that said things like, subduction stimulates erogenous zones. Now that looks a lot racier than it is. It just means that when one plate sinks under another, you get zones of mountain building. Yeah, but yeah, still, all right, you get it, you get it. Okay, so you get subduction zones when a continental plate runs into oceanic crust. And then where two plates are moving past each other, we call that a transform boundary or a transform fault. But what do these things look like? Okay, what's actually happening at plate boundaries is oceanic crust is being produced and it's being consumed. There are, like, the bedrock of the Ozarks ranges from roughly 300 million years old to the oldest rocks in the Ozarks are over 1 billion years old. There's some old volcanic rocks exposed around a little town called Irontown, Missouri, in South Missouri, kind of in the core of the Ozarks. There's almost no oceanic crust that is anywhere near that old. The oldest rocks on the floor of the Atlantic Ocean might be about 180 million years old. Half as old as the rock we're standing on, roughly, close enough. Yeah, the rock that floors the Atlantic Ocean ranges from rock that formed, half as long ago as the bedrock that Conway's built on, all the way to rock that is forming now. There is rock forming right now, building the Atlantic floor. And that new rock is being produced at these mid-oceanic ridges. What happens is that the ridge is where two plates meet. along those ridges, here I'm going to stand in front of the webcam because I'm going to demonstrate this through the means of yoga. Okay, I am a mid-oceanic ridge. Okay, the layer that the plates are riding on, the asthenosphere, that weak layer, almost everywhere it's under very high pressure, and that keeps it solid. But right at the edges of the plates are thin, and water seeping into the mid-oceanic ridge lowers the melting point of hot rock. I couldn't tell you the physics off the top of my head, but it's true. Wet rock melts at a lower temperature than dry rock. And so what happens is right under the ridge, where there's less pressure and more water, you have this pool of melted rock, and that melted rock begins flowing upwards, like this here. I am a stream of melted rock flowing upwards. And as I flow upwards, I push the plates apart on either side, like so. Okay, once I've done that, I solidify and I cool, and now I am solid rock. And now more molten rock wells up from below. And as it wells up from below, it pushes the plates apart. And then we plie in fifth position. Actually, I'm kidding. Ow. We don't plie in fifth position. Not anymore, we don't. And the process is called seafloor spreading, where older crust is constantly being pushed aside in both directions as liquid rock pushes its way up from below, solidifies, and forms new crust. So new crust is constantly being made at these mid-oceanic ridges. And because hot rock expands, that's why this happens in a ridge in the first place. So that's where the major mid-oceanic ridges are. You can see there's that mid-Atlantic ridge coiling down like that. There's seafloor spreading here at the southwest Indian Ridge. That ridge right here is sometimes called the 90-degree ridge because it's at 90 degrees east longitude. The East Pacific Rise is right here. The Galapagos Islands are right there where three ridges happen to meet. Okay, you can see where they are. They're these red lines. As you might expect, when this is happening, it's not a very smooth process. There's not enough WD-40 to lubricate these plates. So you get earthquake activity here, as we saw. And there's a cross-section of what it looks like. Liquid rock, or magma. Liquid rock is magma if it's below the surface, and lava if it's on the surface. And it's not just because we like using annoying names. There's actually some differences in chemical composition. Lava tends to lose dissolved gases and water that were present when it was magma. Anyway, so here's magma welling up from below, pushing its way into the gap between tectonic plates, pushing those tectonic plates aside and hardening into new rock, new crust. So plates are growing here and being pushed to either side. And I didn't mention it, but with GPS, it's actually possible to measure how fast this is happening. Your GPS units don't have this kind of accuracy, but with more sensitive receiving stations, you can pinpoint the location of points on the Earth literally down to the millimeter. You know, mine thinks I'm on the frontage road instead of the interstate half the time. But if you buy the stuff that the big boys get to play with, you know, this is how the military sent its cruise missiles right down Saddam Hussein's chimney. Or would if he were still around, which he's not. Anyway, Um, where was I? Right. You can get millimeter scale accuracy with a really good GPS base receiving station. And it's been possible to use these to measure how fast the continents are moving apart. And it depends on where you are, but it ranges from between about 2 and 20 millimeters a year. This is roughly the speed at which your fingernails grow. Some areas it might be as fast as the speed of your hair growing. But yeah, you can actually measure the distance between a point in North America and a point in Europe, and they do in fact get farther away from each other at a rate of between about 2 and 20, actually I think it may be centimeters instead of millimeters now that I think about it. Yeah, that's a little more, yeah, that's right. 2 to 20 centimeters a year. You know, a couple of inches each year is how fast this process is going on. We don't have time to get into how we do the trick, but there are ways that we can calculate a calendar age in years for certain types of rock, mostly using naturally radioactive elements in the rocks. This is a technique called radiometric dating. This is where we get all of these millions and billions of year dates that we throw around. I don't know if I have time to explain how it's done. Maybe I can work it in later if anybody is really curious. But it's been possible to date rock samples taken up from the deep ocean. And different dating techniques all converge on this. The youngest rocks in the Atlantic Ocean are shown in red, and they're right on that ridge. They're the rocks that make up the ridge. The very youngest rocks are the ones that are forming now, somewhere on the mid-oceanic ridge. They get older in either direction as you go away, and the very oldest parts of the Atlantic, shown here in blue, next to Africa on one side and North America on the other side, the oldest those get is roughly 150 million years. There's no oceanic crust anywhere on the Earth's surface that's older than about 210 million. See, the continents aren't subject to this because the continents are not on these ridges. So rock on the continents can be much, much older than this, but seafloor crust is constantly being created, and as we will see, it is constantly being destroyed as well. New crust is always being made at the ridges, old crust is constantly being destroyed. By the way, maybe you can see this a little more clearly, that if you push the edges of the continental shelves of Africa and North America, they actually fit almost perfectly. One odd little corollary of this is that when Africa and North America were joined, and when they split, the bedrock on the Atlantic side of the Appalachians used to be a part of Africa and ended up going with North America instead. One of these pieces of African crust that ended up glommed onto North America is up here. It's called Plymouth Rock. Supposedly the rock that the Pilgrims stepped on when they stepped forth from the Mayflower out onto the shores of the New World. So yeah, Plymouth Rock is technically African American, which I think is kind of strangely ironic but cute. Right. Carry on. In the 50s, scientists started towing magnetic field detectors over the ocean floor. This is one way to find hidden submarines, by the way, because submarines being made of steel have a magnetic field. Modern subs, I'm told, actually have ways to cancel their own magnetic field. I don't know how they do it, and if I did, I'd probably have to kill you, but it's true. But yeah, magnetic field detectors are a way to try to detect subs. And scientists began towing these over the ocean floor. And this is weird. It turns out that in some areas of the crust, the rocks have, well, okay, rocks of the crust have their own magnetic field. In some areas of the crust, the magnetic field of the rocks is pointing in the same direction as the magnetic field of the Earth. In other areas, the magnetic field of the rocks is pointing in the opposite direction as the magnetic field of the Earth. It actually cancels out the Earth's magnetic field. And what's even weirder is that these zones form stripes running parallel to the rifts, and the zones are symmetrical on either side of the rift. In fact, they look like that. So in red right here, there's the ridge today, and those are the rocks that formed most recently. The orange areas on the other side are zones of rock where the rock's magnetic field is opposite from the Earth's current magnetic field. And then in green, that's rock that's pointing in the same direction as the Earth's magnetic field. And then in blue, there's rock that's pointing in the opposite direction as the Earth's magnetic field. And you see they make these stripes that are parallel to the ridge and are symmetrical with respect to the ridge. Right? See what I mean? Sort of, kind of? Okay, the reason is that the Earth's magnetic field periodically reverses itself. If you got an Earth compass today and then went back in time, I forget, 50,000 years or so, you would find that the north pointing needle would point south. Because there was a time about 50,000 years ago when the Earth's magnetic poles were the reverse of what they are now. A compass made for today's poles would have pointed south instead of north if you could take it back in time. So the reason for the stripes is that when igneous rocks form at that mid-oceanic rift, once they cool below about 600 degrees Celsius, a temperature called the Curie temperature, they get magnetized by the Earth's magnetic field. Right? If you take something with iron in it and you put it in a magnetic field, you'll make it magnetic. Anybody ever do that? Take a paper clip, stick it to a toy magnet for long enough, and then take off the paper clip, and you'll find the paper clip is now magnetic. Try that sometime. It's easy. Yeah, the reason for that is that something that's a diamagnetic material in a magnetic field will pick up the field. So you take something made of iron and you expose it to magnetism, and that thing made of iron will become magnetic itself, and it will have the same magnetic field in the same direction. So rocks, as they form at the Earth's crust, pick up the magnetic field of the Earth, and even after the Earth's magnetic field flips, the rocks that have formed will keep whatever the magnetic field was at the time that they have formed. So if you think about it like this, there's a mid-oceanic ridge. In black right here, we have rocks that formed when the Earth's magnetic field is in the direction that it is now. Right? In fact, right along the ridge, those are rocks that are forming now. And they pick up the magnetic field that the Earth has now. The white areas are rocks that formed in the past when the Earth's magnetic field was flipped. So you can think of these rocks as having little frozen compasses inside them that are pointing south. The frozen compasses being the magnetic fields of atoms of iron in them. There's lots of iron in oceanic crust. And you should be able to see what I mean by the pattern being symmetrical. Right? It's symmetrical because rocks form in these directions. The newest is right at the ridge, and then the newest rock gets pushed aside by even newer rock that's coming in. So the newest is always at the ridge. Older rock is pushed away in either direction. Am I sort of making sense with this? This is tricky. Okay, I tell you what, on Monday I'll come in with a couple of rolls of paper towels and give you a proper demonstration of how this works. Right, there's the stripes. Okay, if new crust is being formed, either the Earth is blowing up like a balloon, which, by the way, it isn't, or crust must be destroyed at the same time that it's being created. And oceanic crust is destroyed where one plate sinks under another, and we call those areas subduction zones. And subduction zones are marked by oceanic trenches, and they're marked by structures called island arcs, or sometimes they're called volcanic arcs. And I'm really starting to get my second wind, and I would love to keep going, but it's 1:50. So by the power vested in me by the state of Arkansas, I thought we'd get a little farther, but I'll stop there. And I'll come back on Monday with some rolls of paper towels and give you a better explanation of seafloor spreading. And I'll come over here and stop the recording. And let me see, do I have any? Okay, I am not seeing any questions here on the chat. Do I have any questions from our live audience? All right. Okay, so I will go ahead and stop recording, and I'll see you folks on Monday.